Alright, now on to calculus identities. So how can we use mathematical induction to prove a specific calculus identity? And we're going to focus on one of the first calculus identities that you saw. That is, the derivative of some x to the n is n outside times x to the power of n minus 1. So this was like the first calculus algorithm that we learned. You know, you take the power, bring it out the front, and you drop that power by 1. But before we get into the proof, because that's what we're trying to do here, right? Prove this. Let's just take a bit of time to understand how we came up with this in the first place. Like, we're so used to using this now, but what did we do to arrive at this rule in the first place? Well, we started off with approaching from first principles. So we took this function here and we made it a limit as h approaches 0. And this is giving us the gradient of the secant, right? But as h approaches 0, our secant got closer and closer to being the real tangent that we were after. And so, yeah, this first principles is where we started. And from here, we analysed a whole bunch of different functions using first principles, and we saw that in each case, when we derived them, we got this process occurring continually. We noticed a pattern where the power would come out the front and then the power would reduce by 1. And so because we did a number of these using first principles and we noticed the pattern, we said, well, it looks like in general the power comes out the front and we reduce the power by 1. But is that really proving something? No, it's not. So just a little refresher of how we sort of first introduced you to this rule, but now we're going to use mathematical induction to prove it. So step 1, prove true for n equals 1. So let's start with the left hand side, which is the derivative with respect to x of x to the power of 1. Or we could just write this as the derivative of x. Now, this is subtle, but it's key. We can't go and use this rule that we already know, because that's what we're trying to prove. So how else are we going to come up with what the derivative of x is if we can't use this rule? Well, this is where we can think about what the derivative actually means graphically. It's just the value of the gradient, right? Or the gradient of the tangent. And what type of function is x? It's just a straight line with a gradient of 1. So we know that the derivative of x is 1 because the gradient of y equals x is 1. So for this specific case, right, it's a good idea to actually state our reasoning for why the derivative is 1, because we're not using the standard algorithm. Alright, let's move on to the right hand side. So the right hand side is n times x to the power of n minus 1, so that's 1 times x to the power of 1 minus 1. So this is 1 lot of x to the 0, and that's just 1. And so that equals our left hand side. So we've done step 1. This is therefore true for n equals 1. So let's move on to step 2. Assume true for n equals k, where k is also some natural number. So we're assuming that the derivative with respect to x of x to the power of k now is k times x to the power of k minus 1. Alright, step 3. Prove true for n equals k plus 1. So what is it that we're required to prove? Well, the derivative with respect to x of x to the power of k plus 1 now is equal to k plus 1. So we're replacing the k with k plus 1. So I'll just put it in brackets. Times x to the power of k plus 1 minus 1. Right, so let's just say that that's x to the power of k. So k plus 1 minus 1, the 1's cancel. So this is what we are now required to prove in step 3. So let's start with our left-hand side. That is the derivative with respect to x of x to the power of k plus 1. So what are we going to do with this? Well, remember, we want to use step 2. Okay, so we can see the link, hopefully, between x to the power of k plus 1 and x to the power of k. So let's go ahead and split this up using our index laws. So we have x to the power of k times x. Right, if we combine these back together, the k and the 1 in this power would just add together. Okay, but we've gone the other way. And what we have here is a product rule. Right, we've got the derivative of one term times another term. Right, typically we talk about it as u times v. So we're trying to find the derivative of this. So our product rule tells us that we have uv dash plus vu dash. Right, so if this is our original function, u times v, then our derivative is uv dash plus vu dash. Now before we go any further, it's probably a good question if you ask, hang on, why can we go ahead and use the product rule when we're trying to prove this initial calculus identity that we first started with? Like, we can't, if we go back to step 1, we weren't even allowed to say that the derivative of x is 1 using this algorithm, because that's what we're trying to prove. So why now are we allowed to use the product rule to help us? And that's a really good question, but the thing is, the product rule is separate to this particular identity that we're going to prove. So in order to answer this question, what I'd like you to do is to actually go and watch one of the videos from 3 Blue 1 Brown. I'll provide a link, and it's one where Grant Sanderson is explaining about how to view calculus and how to view some of these rules, such as the product rule, not through the algorithms that we're used to, but how you can almost generate it geometrically, and it's really cool. So it's just watch from 4:10 to 8:40. Okay, so just 4.5 minutes, but really, really useful. So I encourage you to go and watch that now, actually. So use the link provided, go and watch that now, and then come back and we'll keep going with the rest of this proof. Alright, so hopefully that video from Grant helped you understand why the product rule can be viewed separately to the calculus identity we're trying to prove. So let's go ahead and use the product rule now with this specific setup. So we have our uv dash, or our first function, x to the k, times the derivative of our second function, okay, our v, so in this case derivative of x, plus and then we switch it round. So we have our v, or our second function, so x times the derivative of the first one, so the derivative of x to the k. Alright, let's think about what we've seen previously. So in step 1, we already stated that the derivative of x is just 1. So we have x to the k times 1. And then we can use step 2, which says that the derivative of x to the k is k times x to the minus 1. So we've got this x here, and then we can use step 2 now and replace this with k times x to the power of k minus 1. So this is where we're using our step 2. Alright, let's go and tidy this line up a little bit. So x to the k times 1, well, that's just x to the k. And then we have this second term. So what's going to happen here? Well, we've got an x term times another x term, so we can add the powers. Now this is just x to the power of 1, right? So we have k minus 1 plus 1. So all we end up with is k times x to the k, right? Because the minus 1 and the plus 1 cancel out. Now, can we simplify this line? Yeah, we've got a common factor of x to the k, right? So that leaves us with 1 plus k in the brackets, and if we just rearrange this to make it look like the right hand side we're after, we have k plus 1 times x to the k, and that's it. We've reached the right hand side. So we have shown that this is true for n equals k plus 1. And then we finish off with our standard statement. So well done, you've just proven this calculus identity that you use all the time, and you know it's just a simple algorithm for us now, but we have now proven it using mathematical induction, which is pretty cool. Alright, well done guys.